Hey everyone, welcome to The Explainer. I'm absolutely thrilled you're here today. We're going to uncover the hidden mathematical journey of something you probably do, hundreds of times a day without a second thought. We are going to explore exactly how a computer reads what we type. It's a full macro to micro journey, starting from those literal plastic keys right beneath your fingertips, all the way down to the microscopic electrical signals that your computer's processor actually understands. Okay, so here's our roadmap for today. First up, decoding the keyboard. Then, the universal alphabets. Third, the language of machines. Next, shortcuts for huge numbers. And finally, translating between systems. Let's jump right in.
To really set the stage for how profound this all is, I want to share this incredibly powerful quote from Albert Einstein. He pointed out that our ability to count and these foundational number systems we've built are the absolute bedrock of every scientific discovery. And as we'll see today, these systems, they're also the beating heart of all modern computing. No numbers, no tech. It's really that simple.
Seriously, I want you to look down at your keyboard for just a second. Think about the massive, and I mean massive, language barrier between you and your machine. You see human-readable letters like A, B, and C. But computers, well, we know they only understand a binary language of zeros and ones. So how on earth does physically pressing a plastic key cross that giant language barrier?
Let's get into it. Section 1. Decoding the keyboard. Let's ground this abstract concept with an everyday action. When you press the uppercase letter A on your keyboard, the computer absolutely does not see a shape with two slanted lines and a crossbar. Internally, that specific key press is immediately mapped to a unique decimal value. In this case, the number 65. So, irrespective of the make or model of your keyboard, hitting capital A essentially just shouts 65 at your system.
So the really crucial point here is understanding a concept called encoding. Encoding is basically the mechanism of converting data into an equivalent cipher using specific codes. Think of it as the ultimate translator or dictionary sitting right between you and the processor. You hand it an A, and it hands the computer a 65. This standard dictionary makes sure your computer doesn't accidentally mistake an A for, say, an exclamation mark or a space. Which brings us to Section 2, the universal alphabets.
Back in the early 1960s, computers actually had no standard way to talk to each other. It was kind of the Wild West. That led to the creation of ASCII, which used just 7 bits, meaning it could only represent 128 different characters. Now that was totally fine for basic English, but what about the rest of the world, right? That's exactly why Unicode was developed. It's amazing, really. Unicode assigns a unique number for every single character in every written language on Earth, everything from English to the Devanagari script used in Hindi. In fact, if you type the Hindi alphabet Unicode maps it to a unique value, specifically 0905. Talk about an upgrade.
Let's actually spell it out and look at how ASCII handles a simple English word. Take the word data. The computer reads this character by character. First, D maps to 68. Next, A maps to 65, T maps to 84, and the final A maps to 65 again. So, to a computer, text is quite literally just a sequence of decimal numbers standing in a line.
Moving right along, let's hit Section 3, the language of machines.
Okay, to really understand computing fundamentals, we have to look at the 4 core positional number systems. A number system is just a method to represent numbers, defined by its base. We use the decimal, or base 10 system, counting from 0 to 9. But computers, they use binary, base 2, which is just 0 and 1. And to help manage the incredibly massive binary numbers that result from that, computer scientists introduced octal, base 8, and hexadecimal, base 16. Let's compare our human reality with the machine's reality for a second. We naturally use base 10, but a computer's integrated circuits are made up of millions, sometimes billions, of microscopic transistors. And these transistors act exactly like tiny light switches that can only be in one of 2 states: on, which is a high electrical signal, or a 1, and off, a low signal, or a 0. Because the physical hardware literally only has 2 states, the math can only have 2 digits, 1 and 0.
So remember our uppercase letter A, the one our encoding dictionary translated to the decimal number 65? Well, to make that A physically exist inside those transistors, that decimal 65 has to be converted into this exact 7-bit binary string, 1, 0, 0, 0, 0, 0, 1. This is it. This is the absolute rock-bottom layer of the digital world.
All right, Section 4, shortcuts for huge numbers.
Because, let's be honest, staring at endless ones and zeros gets very confusing very quickly.
Developers created a genius shortcut. We group them into chunks. If you group 3 binary bits together, you get 8 possible combinations, giving us the octal system. But much more commonly today, we group 4 binary bits together. This gives us 16 possible combinations, which is the hexadecimal system. Now, hexadecimal uses numbers 0 through 9 and then alphabet letters A through F to represent 10 through 15. This is a total game changer for things like 16-bit computer memory addresses. A giant, clunky binary address like 1100000011110001, it can be compacted down to just 4 characters in hex, C0F1. So much easier for a human to actually manage. And here is a brilliantly practical, everyday application of this exact shortcut. Hexadecimal codes are the absolute standard for describing colors on web pages. To render the roughly 16 million colors your monitor can display, we mix 8 bits of red, 8 bits of green, and 8 bits of blue. But instead of writing out 24 tiny ones and zeros for a single color, we just write it in hex. Pure white, which turns all pixels fully on, is perfectly represented as FF, FF, FF. Every single pixel color you are looking at on your screen right now is being determined by these compact hex codes. Pretty cool, right?
And finally, Section 5, translating between systems.
So how do we actually do the math? There is this beautifully simple, universal 4-step recipe for converting our human base 10 numbers into any other system, whether it's binary, octal, or hex. Step 1, you divide your decimal number by the base value you want to convert to. Step 2, you note the remainder. Step 3, you take your answer, the quotient, and keep dividing it by the base, noting the remainder each time until your quotient finally hits 0. And Step 4, the magic step, you write all those remainders out in reverse order, from bottom to top.
Let's actually prove this using our letter A, decimal value 65. We want binary, so we're dividing by base 2. Okay, 65 divided by 2 is 32 with a remainder of 1. We keep dividing. 32 divided by 2 is 16 with remainder 0. 16 by 2 is 8 with remainder 0. We keep doing this all the way down to 0. The remainders, read top to bottom, are 1, 0, 0, 0, 0, 0, 1. But remember step 4, we read them in reverse, from bottom to top. Actually, you know what? Scratch that. In this highly specific case, it's a palindrome, so reading it in reverse still yields 1, 0, 0, 0, 0, 0, 1. But either way, we have mathematically proven exactly how your physical keystroke becomes a sequence of transistors being toggled on and off.
And that brings us to a seriously mind-boggling realization. We just spent this entire explainer tracing the complex, mathematical journey of a single letter A on your keyboard. It required dictionaries, encoding standards, base conversions, and binary translation just to turn one single letter into 100001. Now think about this. If a single keystroke requires all of this math, how does an entire high-definition video with millions of pixels, synchronized audio, and millions of colors boil down to these exact same rules of ones and zeros? It is an absolute marvel of modern engineering, and it all starts with the humble mathematics of number systems. Thank you so much for joining me on this explainer. I really hope this changes the way you look at your keyboard forever. Keep learning, and I'll catch you next time.